All right. So yeah, today we are going to finish phylogenetic trees. We are going to see two algorithms, UPGMA and neighbor joining. And I hope this spring break was useful. Yeah, being locked up at home was not probably good. So it defies the purpose of spring break, right? Yeah, this one. Okay, but anyway, I mean, it was good for me. I had some work to do, which was piling up. So this spring break allowed me to finish these works that are in the pipeline. So it was good for me anyway. I hope it was good for you as well. So I mean, having this 9-day break was also, I mean, you may have forgotten what we were talking about in terms of the topics we were talking about in this class. The problem that we were trying to solve as a small reminder. So we are given a distance matrix between species or genes or these A, B, C, D, which by the way mean they are the same thing. The lowercase a doesn't, I mean, it's actually confusing. It should have been uppercase A as well, all these here, or they should all have been lowercase letters. They mean the same species, so this A and this A is the same thing, B and B is the same thing. So we are given uh, an all-to-all pairwise similarity matrix, or maybe a distance matrix. It may be the edit distance between genes, or it may be the similarity score converted to some uh, distance measure. So we are given pairwise distances, and this is something that is easy to compute. It may take a long time to, if you have, for example, your number of species or genes that you want to get this all-to-all distance matrix for is like on the order of tens of thousands. You may have, for example, want to have the phylogenetic tree for all the genes in the human genome. So there are like 25,000 genes. If you're going to look at different isoforms, transcript, there can be up to 50,000 transcripts that you may be dealing with. So this matrix will be, in that case, a huge matrix, 50,000 by 50,000. So you're going to be looking at 2.5 billion, right? Yeah, 2.5 billion entries in such a matrix, 25,000 by 25,000. So it's a huge matrix. And also getting all these pairwise similarity scores may take a long time, but still finding, if you think about filling the single cell, how do you find the similarity between B and D? You either use pairwise sequence alignment, or you have some measure that you can compare between these two. It's easier than trying to get the entire picture at one shot, considering all the combinatorial relationships between them. So using pairwise, looking at pairwise relationships is always tractable. It's polynomial in time. I mean, it's the number of all possible pairs in n objects is n choose 2, which is O(n) square. So it's doable. All right. So getting this matrix, we will, although it may take a little bit of time, it's still doable. All right. It's not an NP. This part is not an NP complete problem. The difficult problem is that given this matrix, can we find a tree? Can we arrange them in a tree in such a way that the leaves of these leaves of this tree is going to be these objects, and this is going to be a weighted tree in such a way that the tree paths will be equal. The distances on the tree paths will be equal to the distances we have here in this matrix. So this is an NP complete problem because we have to look at all combinatorial grouping of all these things. There may be some greedy heuristics which may not work for all the input cases. We are going to see such heuristics today. UPGMA is one heuristic which makes lots of assumptions, like all the species, all the objects that we are trying to cluster or grouped together in a phylogenetic tree, they're all equidistant from the root node. It's based on this assumption. This is a big assumption, right? I mean, it's like there was a single hypothetical ancestor, and every species that we have today, they evolved at the same time from that hypothetical ancestor. It may make sense in certain settings, but we see that this is not, for example, true for this one. So for this one, for example, the distance uh, of A to root node is 4, while the distance of B to the root node is 6. As you can see, 3, 2, 1, 1, 2, 3, it's 6. Distance of B to the root node is 6, while distance of A to the root node is 4. And this one is, for example, 8. Distance of E, which is on the same branch. I mean, they have a same parent, and their distance to the root node is different. Okay, so some of these assumptions these are like greedy choices or some algorithmic assumptions that make the algorithm to work fast or and to generate some tree at the end. Okay, so let's start with the UPGMA algorithm, and the general outline of these algorithms. Any of these algorithms that we are going to see, they're called agglomerative clustering algorithms. Agglomerative. It means by combining small things into agglomerates, it means bunch up together. So it starts with each object. So this is agglomerative clustering. By the way, the phylogenetic tree algorithm that we see here today can also be considered as a hierarchical clustering algorithm, which we're going to also see when we talk about microarrays, analysis of analysis of expression data. We're going to again revisit this topic. So the clustering algorithm, there are two main approaches. So this agglomerative clustering, on the other hand, there's also the divisive clustering, or it may have a different name. I haven't used this a lot, but what it means is that in this one, all the objects are in the same cluster. So you have n objects, and you try to find a way to divide them into two. And each time you get a new subgroup, which is roughly half the size of the other one. Maybe it's not half the size, depending on how the objects actually naturally group together. I shouldn't say n over 2. Let's call it m and k, for example. Two different sizes, but these subclusters are obtained by dividing the original single cluster into subgroups like this. So this is a way to cluster the objects as well, but by dividing them at each iteration. So both of them are iterative clustering methods. At iterations, iteration 1, iteration 2, iteration 3, at different iterations, we make certain actions which is going to change the current clustering. It will start with a single cluster, then two clusters. If it's a parallel algorithm, we can work simultaneously on these subclusters. If it's not a parallel algorithm, for example, in iteration 2, we deal with this. In iteration 3, maybe we deal with this cluster and divide it into 2. So this is the divisive way of clustering, which we are not going to consider in this course. So in agglomerative clustering techniques, the idea is to go bottom up, start with n different clusters. Each object, if we have n objects, n species, n genes that are given to us, we start with each of these objects as individual clusters of their own. And at each step, at each iteration, we decide which two of these clusters, okay? I mean, they're individual objects initially, but at an intermediate step, we'll basically have a number of clusters which may contain single objects, multiple objects in them. So at an intermediate iteration, you're going to have a bunch of clusters. Now, at this iteration, we have to decide on which two clusters to combine. together as a single cluster for the next step. Okay, so in this sense, we start with n clusters. In the next iteration, we are going to end up with n minus 1 clusters. Since we divide these into two, it becomes a cluster on their own, and we don't deal with these individual nodes in the next iteration. They become a single cluster that is going to be dealt with later. So this is similar to that multiple sequence alignment algorithm, like the progressive multiple sequence alignment. Every time we find the most similar two sequences, we combine them, and then uh, we remove the individual sequences, we replace them with their profile. The idea is the same. So it's going to take the number of iterations that it's going to require is n, because at every iteration we remove two clusters, we merge them, the merged cluster is inserted into the pool. Now, and it goes on until we have a single cluster remaining at the end. So since at each iteration we choose to combine two, you may ask, why don't we, for example, combine three of them in single iteration or four of them? It's just an algorithmic decision, okay? So it makes it easier to work on again. I mean, if you want to say combine triplets of clusters into single nodes, you immediately increase your algorithm's complexity to O(n) cube, because at each iteration you have to look at all the possible triplets to combine, and this is n choose 3 is O(n) cube. But yeah, if you choose which two to combine, which is, I think, the smallest case, which will give you O(n) square choices at each iteration. And then you combine them. You continue doing this until all of the objects are combined together into a single cluster. So both the UPGMA and the neighbor joining algorithm has this general structure. Okay, UPGMA neighbor joining, they have this general structure where we combine individual items into a single cluster. Now, as obviously we have to, these two algorithms are different from each other. We have to make, while we are doing this, let me get a new slide. We have to, how we decide on which two clusters to combine. And while we're combining them, there's another thing we are doing. It's not only a clustering algorithm. Both UPGM and neighbor joining, they need to decide on a certain thing. The first thing is when we combine two objects like I and j, we are not just only combining them to a new node named ij. We also decide on edge weights on this tree. X, let's call them x and y. We want to figure out what this x should be, what this y should be. All right, so this is another thing the algorithm has to decide. Every time it's combining this, it is removing I and j from our list of clusters and adds this ij as a new combined supernode into the cluster. And it has also need to decide what these edge weights should be on the tree. This is one thing they need to do. Another thing that is really important is after we add this ij, but if you remove this individual I and j from the list of clusters and we add this to the list of clusters, what it means is that in our distance matrix, these individual I and j's, the rows that correspond to them, they are removed. So the row corresponding to I and j and the corresponding columns are also removed. So they're removed from the matrix. Instead, our matrix is now an n by n minus 1 by n minus 1 matrix, which we have a new object now. ij, this combined cluster, is now a new object in our distance matrix. Therefore, we need to know what is the distance of ij to some particular other node k. Okay, so we need to also decide on this. These are the things that needs to be decided when we are, so in other words, it's like, what is the distance of a cluster to an object? So this k, by the way, it can also be another cluster on its own, because at some intermediate iteration, we will have ourselves some clusters of objects. So K itself may be a cluster. So we need to decide if we are given two clusters like this, which may contain some objects in them, individual objects. This one contains, for example, 6 objects. This one contains 3 objects. We need to decide on how do we compute the distance between two clusters. That's one thing is this, how do you define, and again, as an analogy to multiple sequence alignment algorithm, this step was not that difficult, right? Because we know how to align a profile against another profile. So we just use again the pairwise sequence alignment and use the profiles of these sequences and align them to each other to find this distance. But if we have these individual objects, if you're given this matrix, for example, if I tell you that I have a cluster which contains A and B in it, and there's another cluster which contains C and D in it. Okay, so how do you compute if this one contains A, B in it, and this one contains C, D in it? What is the distance between these two clusters is another thing that we need to decide. So these two things, which at each iteration, how do you choose the two clusters to combine? And after you combine them, how do you determine these edge weights on the tree? And this is also how do you determine the distance of the new object to the other objects in your current tree? These are the things that needs to be decided by UPGMA and neighbor joining. UPGMA and neighbor joining, they differ in how they make these choices, how they determine these X and Y, how they determine which clusters to combine at each iteration. But other than that, the general algorithm is exactly the same, the general algorithm outline. We start with individual objects. At each iteration, choose 2 objects, combine them, update the distance matrix, and update the tree. Write these 3 weights, update your distance matrix after removing those individual objects and inserting the new one. The matrix is going to get smaller and smaller at each iteration. So until we have only one object, a single object that is remaining in the matrix, we continue doing this. All right, so let's start with the simple one, the UPGMA algorithm, because both the decisions and the how those weights are assigned, they are really simple decisions, simple ways to compute the weights. So UPGMA is really a very simple algorithm. So let me let me copy this one. So how was it? Yeah, let me copy this one here. Let me resize it. Any questions, by the way, up to this point? I hope everything is clear. Scale width to here, and I'm going to now describe the UPGMA algorithm on this matrix, and you're going to see what kind of a tree we are going to get. I wanted to retain this tree here as a reference to see UPGMA is going to give us a different tree. Right, now I got my pen. Oh, by the way, I think yeah, the whole canvas is visible now. All right, so the first thing that UPGMA does, which 2 clusters to combine, is a really simple greedy decision. The 2 objects that are closest to each other, which with minimum distance between them, you choose those pair of object to pair of object to combine. For example, we look at this matrix. What is the minimum value in this matrix? It's 4, right? But there are 2 4s. BC, the distance between B and C is 4. The distance between B and D is also 4. So when we have ties, so this is a tie, and we break ties randomly. So which means that you can, at this iteration, the first iteration of the algorithm, you can choose to combine BC or BD, doesn't matter. All right. So which one do you want to choose? Any suggestions? Should I choose BC or BD? It will. It may give. By the way, it may give you a different tree at the end, or maybe not. I'm not sure. If we break ties randomly, yeah, let's start with BC. I'm not. I think it shouldn't matter which one we choose in UPGMA. So let's start with BC. 2 votes for BC, 0 votes for BD. So let's start with BC. So what we do is very simple. We write B, C, and we combine them together. I will have these intermediate nodes as square and the other leaf nodes as circular like this. Now I have a new node BC. And what I do is in UPGMA, I need to decide what these X and Y are, right? What it does is this. The distance between B and C, which was 4, is divided right at the center equally. And whatever branch we have here, 2 and 2, is written here as 2 and 2 like this. Okay, so everything is the distance to their parent nodes is equal. By the way, when we are doing this, we are going to see that it's this distance that we are dividing into 2. It's actually the distance to the root node. Right now, BC is the root node. We are going to see how, at some iteration of the algorithm, you're going to see that, oh, you have divided into 2, but why didn't you put 2 there? You are going to tell me that. Why didn't you put 2 there? Because this 2 will be the total distance all the way until the root node. So whatever is remaining, I'm going to put there. So you'll see what I mean when we come to that iteration. But basically, we divide the individual distance between B and C into 2, and we give equal distances on the three edges like this. Now, the next step, what is the distance of BC to the others? For that, UPGMA has this very nice, which is called like average linkage clustering. If you have 2 clusters, let's call it cluster 1 and cluster 2, for all X that is a member of cluster 1 and for all Y that is a member of cluster 2, what we do is we sum the individual distances between those objects, and we divide the summation by the size of the multiplication of the sizes of these clusters. So this is basically, I'm taking the average distance between individual members. But one thing that is really important here in this, usually that's the place where the students make mistakes in the exam, is at an intermediate iteration of the algorithm, you don't just look at this current matrix to figure out these averages. These averages, as you can see, they refer to the individual objects in the original matrix. So when we are computing the distance between 2 clusters, we are always referring to this initial matrix which contain individual objects. So for example, if for this particular case, I will have these questions. I have a cluster which contains BC in it. And for example, I have A here. What is the distance of BC to A? What is the distance of BC to E or D? Yeah, I have D and BC to E, right? So I need to compute these three things. I need to compute these 3 distances, and it's simply, basically, let me also write them here. A, B, C, D, and E. A, B, C, D, and E. By the way, the other parts of the matrix that were, only the distances that involve B and C are going to be changed. The others are going to remain same. For example, what I mean is that the distance between A and D was 8. It's going to remain 8. A and E, 7 here. Now, and here is all 0, 0, 0, 0. The distance between D and E is 12. The distance, yeah, these are the other parts. BC and D, BCE and BCA, they need to be changed. So these are how I'm going to compute them. And as I said, it's really easy. It's just an average. It's basically looking at all pairwise, sum up all pairwise distances between these two clusters, between individual objects. Distance between B and A, distance between C and A, and divide it by 2 times 1. Okay, this part is the place where students make an error by, for example, if a cluster contains 2 objects and another one 3 objects, sometimes what they do is they, instead of dividing individual things and dividing that by 6, they Oh, actually, it's like this. Let me give you an example. Imagine in the previous iteration, this one contained 2 objects, this one contained 3 objects, right? Now we are going to compute. We combine them together, and now we are going to compute the distance to this one, right? Imagine this may contain, for example, 4 objects in it. Now, the most common error the students do is, in the previous iteration, we have this distance and this distance already, right? We don't use this. They basically do this. Distance of 2, 4. I mean, 2, 4, when I say 2, 4, distance of the cluster which contains 2 objects in it, and distance to the cluster which contains 4 objects in it. But we had these in the previous iteration. In this iteration, we chose to combine this into this one. So they basically do this, which is not correct. Divide by 2. Okay, this is not the formula for UPGMA cluster computing. What we need to do is we need to sum up so this one is now a cluster with 5 objects, because if you do it like this, you don't give a higher weight. This cluster contains 3 objects in it. When you're computing its distance like this, you're giving the same weight to the distance with for a cluster with 2 objects in it. So if a cluster contains more objects in it, I mean, we cannot use this direct distance between 2 clusters when we're computing the average. What we need to do is, instead of using this, so this is a big no, we don't do it like this. Okay, we don't do it like this, but we do it like here. So we have a cluster with 5 objects in it. So for all those 5 objects and for all those 4 objects in the other one, I add up 20. So 5 by 4, there are 20 distances that I will be computing, and I divide this by 20. This is what the formula tells me, okay? I will always refer to the individual distances. We are not averaging, we're not just dividing by two previous distances we had in the previous iteration. This is a very common mistake the students do. All right, therefore I warn you at this point that when we're computing distances between 2 clusters, we're always referring to this initial matrix with individual objects. It's basically average linkage clustering. Sum up the distances between all pairs of individual objects. This is very important. Individual is the bold here. It's important. Sum up the distances between all individual pairs, and whatever number of pairs you have summed up, divided by that. Okay, so 5 here, 4 here. There are 20 pairs between 2 clusters, so you divide this by 20, and that's your distance. So in the initial iterations, it's really easy, right? I have B, C, and A. It basically means that the distance of B and A plus the distance of C and A divide by 2. So the distance of B and A was 10. The distance of C and A was 12. So this one is going to be 11. Okay, 10 plus 12 divided by 2. Now, the distance of BCD, the distance of B to D is 4, C to D is 6. So 4 plus 6 divided by 2, it becomes 5. and the distance of BC and E, 14 and 16. Again, sum them up, 30, divide by 2, 15. So this is, at this point, I'm finished with this current tree, and with this current matrix, I am finished with the first iteration. This is how my tree looks like at the moment. By the way, at some intermediate iteration, you may not have a single tree, but a forest, which means that your tree may not be connected. What I mean is that what happens in the second iteration, for example, I choose to combine A and E. If you choose to combine A and E, it's not going to be attached to this existing tree, and it will be two separate trees growing together. It may be like that. But at the end, when we come to the final iteration, everything is going to combine together into one single connected tree. Now, let me copy this part into a new slide and continue from there. File new. So we are done with the first iteration. Now we're going to the second iteration. And it's the same, basically. We are going to repeat what we have done for all the iterations. Now I have 4 objects. BC is just, I treat it as a regular single object. But when I'm computing the distances between clusters, I always need to refer to the individual objects. Now, in this case, we don't have a tie. BC and D has to be combined. So, right, here, the tree look like this at the moment. BC, I have B, I have C, and 2, 2. Now, BC and D is going to be combined together into a single node like this. All right, that's what. Now, here is the part where we are going to divide this 5 into 2 equal parts, 2.5 and 2.5. And this 2.5 refers to the distance from its parent node to the combined nodes, but we don't put 2.5 here. Okay, again, that's a big no. This 2.5 refers to the distance all the way to the leaf node from this BCD, which means that from this BCD, I'm going to write 2.5 here, that 5 between BC and D is divided equally into 2 parts. 2.5 is written here, and 0.5 is written here. Why? Because this 2.5 refers to the distance all the way to the leaf nodes. Since I have 2 here from this intermediate node to the leaf nodes, the only remaining part out of that 2.5 is 0.5. Then that's why I write 0.5 here. Okay, if I write 2.5, that will make the algorithm worse. Distances will accumulate a lot, and it will be far off, way off than the original distances in the tree. Okay, so this is an important again thing you should note. When we divide this 5, BC and D is going to be combined. Let's combine them. We have the distance between BC and D is 5 here. We divide 5 equally into 2 parts, 2.5, 2.5, and the 3 distances are decided by writing 2.5 from that BCD parent node to the branch that we had just inserted all the way to the leaf node. All right, so the current tree looks like this after we combine D with BC. Now, I need to change my matrix again. Let me go back to my black color. Okay, A, B, C, D, and E. Okay, now I will have a 3 by 3 matrix. A, B, C, D as a single node, and E. So let's see how it's going to look like. It's going to only have 3. I mean, since it's symmetric, that's why I'm always using these parts, or we could have used this part, it doesn't matter. The distance between A and E is 7, and the distance between A and B, C, D. Now, in order to find the distance between A and B, C, D, now at this point, we are going to see why we are not taking students who usually study from the slides at this point will think that we're just taking the average between BC and BD, because that's exactly the same thing in the matrix. It looks like an average, but it's not an average. Oh, by the way, in some points, last year, I remember when we were talking about this matrix, this 12 here, let's see. If you just take a look at this, for example, distance between BCD and A. BC to A is, for example, 5. D to A is 8, right? So 8 plus the mistake that you would be doing if you're not doing it correctly will be to try to take the average of this 8 and 5. 8 plus 5, it's 13, divided by 2, 6 point, so 6.5, right? Now, if you look at this here, if you look at this step here, where B, C, and D are combined together, the distance between B, C, D, and A is written as 10. So probably I'm doing something wrong. So BC, oh yeah, it's not 5. I'm using the wrong numbers, not 5 here. So the distance between, BC to A is 11. And D to A is 8, so it should have been 11 plus 8, which is 19. Divided by 2, it's 9.5. Okay, so but by the way, this is the wrong way to do that, right? Okay, we shouldn't do it like this, because if we do it like this, 11 and 8, we're not taking the average of these two entries. When we're finding the distance between B, C, D, and A, we should just use the individual distances and divide it by 3. We shouldn't, this is the wrong way to do it. So last year, I had some comments from some students saying that, okay, we do it like this, we get 9.5, and since it's written 10 here, they thought that this 10 is the rounded number, that is that 9.5. We always, so while they were studying, they make up this rule saying that we always round to some integers. Okay, this is not correct. We're not if we have some non-integer numbers here, we're going to keep them as non-integers. In no place of the UPGMA algorithm there is rounding. We don't do rounding to the nearest integer. Okay, they thought that the only way to explain this 10 in this matrix was they thought that 9.5 was rounded to 10, which is not correct. Okay, this is false. Because this approach is not correct. We don't just average the two values we had in the previous matrix. What we do is, in order to find the distance between B, C, D, and A, we need to look at these three distances. What is the distance between B to A, C to A, and D to A? Let's go back to our original matrix, which was here. It's 10, 12, and 8. So let's see what will happen when we add 10 plus 12 plus 8 divided by 3. It's a nice round 30 divided by 3, 10. This is how that 10 is obtained, not by rounding. Okay, so this is the correct way to do it. So here we have 10 between B, C, D, and A by using average linkage clustering, the average distance between these two. Now, what is the distance between B, C, D, and E? We do the exact same thing. There is no, what we need to do is add three distances, B to E, C to D, and D to E, and divide it by 3. So 14, 16, and 12. So distance B to E, you have 14, 16, and 12. So let's see what it's 14, 16, and 12. It's 42. 42 divided by 3. Is it 14? Yeah, it should be 14. 14 is just in the middle here. So it's 14 here like this. All right, so this is at the end of the second iteration, we have this matrix, and our tree looks like this. Actually, I have some free space here. I can continue with the next iteration because I'm going to combine, as you can see, the next iteration is going to be simpler, which I will combine two individual objects. Now, I do exactly the same thing. At this next iteration, what is the distance between, what's the smallest distance in this matrix? It's 7. 7 is between A and E. So in the next iteration, what I do is I combine A and E. As you can see, it's not connected to this tree. They are individual subtrees like this. And the 7 is divided into 3.5 and 3.5 like this. Okay? And I need to also compute this in my final iteration. For my final iteration, before I go there, after I combine this, there's another thing I need to do, right? I have two objects now in my tree. After I combine A and E, now I have just this 2 by 2 matrix, which with a just single entry. At the next iteration, since BCD and AE are the only two objects that are remaining, I'm going to combine them together into one single object in the final iteration because they are the only two objects that are remaining. Whatever this number is, it's going to be the smallest non-zero number in this matrix. So how do you find the distance between AE and BCD? AE and BCD. So I need to sum, let me erase this part. I need to sum 6 things. Distance between distance between A, B, A, C, A, D. Oh, look at this. It's going to, I cannot make this 2. But this is decreasing very fast. So the size, okay, left and right decreases really quickly. Okay, so let's sum up those 6 numbers and yeah, let's sum up those 6 numbers now. A, B, C, D, E, B, C, D. Let's refer to my original matrix here. A, B, C. So the 3 numbers are 10, 12, 8. And the others are 14. I already have the summation of these individual items, right? This was 30, this was 42. So what it will be is like this: 30 coming from A to B, C, D, plus 42 coming from E to B, C, D, and divide this by 6. So it's 72 divided by 6, which is 12, right? So here I'm going to write 12. And this 12 is going to be divided into 2 parts as 6 and 6. Okay, so from this final A, B, C, D, E node, a single node, the distance to the leaf nodes are divided equally by 12 divided by 2 is 6. So this 12 is going to be divided equally as 6 on both parts, which means that I'm going to write 2.5 here on this branch, and I'm going to write 3.5 here on this branch. So this is the final tree, and I'm done. So the tree is a little bit crooked, as you can see. The root node did not fit in here. So this is the root node of the tree, and all of the branch lengths are given. I have my individual objects at the leaf nodes, and Again, the 6, as you can see, how it's divided equally, 6, 6 into the two branches. So the, I combined B, C, D, and AE in the final iteration, and it was 6, 6 like this. I did not write 6 and 6 to these branches. The 6 refers to the distance of this combined node all the way to the leaf node. So the entire distance to the leaf nodes is 6 from this root node, equally on both parts. And therefore, there was already 2.5 here. The remaining 3.5 is written on this branch, and there was already 3.5 on these branches. So the remaining 2.5 of that 6 is written here. As you can see, all of the leaf nodes are exactly distance 6 away from the root nodes. So that's one drawback of UPGMA. It will give you a tree with this specific property, with this limitation that all the leaf nodes in your tree are equidistant to the root node. They are not equidistant to their immediate parent nodes. For example, this one is 3.5, this one is 2, but the distance to the root node is all equal for all of the leaf nodes. Such a tree is called an ultrametric tree, and if the distance given to us was such the distance, ultrametric distance, we would obtain the exact correct tree. But if you look at the tree distances, you'll see that it's not, for example, if you look at this one, what is the distance between B and A? It's going to be 12, right? Any object in this branch is going to be distance 12 to A or E. For example, distance of D to A is also 12. Distance of D to E is also 12 on this tree. So in other words, if some of these distances that are here, 10, 12, 8, these are not, the UPGMA algorithm was not able to correctly make the tree distances equal to the distances that are given to us as input. So it gives something approximate, but it cannot give us the exact tree. All right. So if you go back to the final slide of this one, you see that it says it's the exact same tree that we have obtained. This is the produced tree, and the distance of E to B here on this tree is 12, but it's 14 here. Only the distance between A and C and D and E, both of them are 12. It's also correct here, but the other distances, as you can see, are not correctly produced, are not correctly represented in the final produced tree. So it gives something approximate. It does not give, it cannot give the exact tree if the matrix is not given to you, is not ultrametric. Okay, so this was the UPGMA algorithm. Again, the important parts are, it's the decision to combine two clusters. It chooses to combine two clusters that are closest to each other at every iteration, which means that with minimum distance between them at every iteration, and that distance is divided equally among its descendants. And when we're computing the distances between clusters, between AE and BCD, for example, we use average linkage clustering, which has this formula. Okay, the distance between two clusters A and B is simply this. The individual distances are summed up, and we divide it by the product of the sizes of these clusters. All right. This was a really old algorithm, which was first proposed in 1958. It's a scaled tree. This tree we get here is scaled. As you can see, it has edge weights in it. We don't say it's not a scaled tree. We just say that it doesn't give us a tree with the exact distances here. But the problem is that when given an arbitrary distance matrix, it may be impossible to get a tree with the exact same distances as on the input distance matrix. If your tree is not additive, if your matrix that is given to you is not an additive distance matrix, such a tree does not exist. Okay, uh, we will have weights here. It will some of these weights it will be impossible to make a tree such that all these weights are equal to the given distance matrix. Okay, if your input distance matrix is not additive, and in most sequences, the sequence similarity scores between sequences is not an additive score. Yeah, exactly. So it's not a scaled in terms of it doesn't it ignores in a clade where we have these different species. It ignores that they're different. It's not scaled considering the differences of the species inside a clade. You're right in that sense. It's scaled equally. Yeah, it has the same distances. So yeah, yeah. And if you think about it from the root node, yeah, from these, you may think about the scale actually is meaningless. And from a biological point of view, you say that the scale we have here, since it's the same for everybody, it doesn't give me any information, so I can consider this as an unscaled tree. And you're perfectly right. You can do that. There are some distances as you go, but still it gives some information. For example, this difference between, for example, this BCD and AE, at least the intermediate nodes, which may refer to some hypothetical ancestors, these distances are different, right? 2.5 and 3.5. Maybe since it's different, it may give you an idea that, okay, maybe this is 3.5 million years ago, or from 3.5 million years after the first species, and this is 2.5 million years. So there is still some difference in those branches, but still, if you consider the leaf nodes, the entropy is zero. It has the same information. Considering the leaf nodes, all the leaf nodes are equidistant to the root node. There's no difference between them. It means that there is no information there for you if you consider the leaf nodes. But yeah, neighbor joining is going to be different. It's going to give us the exact tree if the tree is additive. But again, this bad thing, this heuristic that, okay, the UPGMA cannot give us the exact tree, then it's a bad algorithm. This is not. This is not a correct way of thinking, because as I said, for certain distance matrices, I can give you a distance matrix, for which getting a tree with the exact distances to that input is impossible. Okay, in that case, remember, what we were doing is we try to find the matrix, we find the tree which is as close as possible. It becomes an optimization problem, and we want to get as close as possible to the input matrix. And UPGMA is just one heuristic in that regard. It doesn't give you way off distances. It gives some close distances. Okay, this is not 10, it's 11. This is not 12, it's 11. Sorry, it's 12. This is not 10, it's 12 in this matrix. This is not 8, it's 12 in this matrix. So for certain values, for example, between A and D, the deviation, the discrepancy is more than we wanted. But it's still not bad. It doesn't give you 4 here. It's 12. But what I say is it's just a heuristic that gives approximate results. And the advantage of UPGMA is it's simple to implement. It's very fast, and yeah, and it gives acceptable results. Now I'm going to have a 10-minute break. As you can see in the actual tree, when you look at the actual tree, you see that decisions we make in UPGMA, some of those decisions are not correct, were not correct. For example, dividing the edge weights into 2 equal parts as 3.5 and 3.5. It wasn't correct, right? I mean, because that 7 has to be divided 1.5 to A and 5.5 to E. So that 7 shouldn't be divided equally as 3.5 and 3.5. That was one mistake. So we are going to see the neighbor joining algorithm after the break, which is going to actually make these decisions differently, considering the path distances on a tree. So if such a tree is possible, neighbor joining is always going to find the exact tree. Okay, if finding a tree is possible, neighbor joining algorithm is going to find the exact tree always. But if it's not possible, then it's still going to give you some approximate close answer to the actual, not the actual tree doesn't exist in that case. It will give a close value to the input distance matrix. Okay, so let's have a 10-minute break now. And as usual, I'm going to just turn off my microphone and stop sharing my screen, but I will keep the meeting on. And I will see you in approximately in 10 minutes at 10:45. So see you all in 10:45. I will stop recording.